Let's now talk about the structure and acidity of alkynes. The triple bond in acetylene, for example, is formed by the overlap of a total of 6 electrons between two carbon atoms. In this carbon molecule, the carbon atoms are sp hybridized, while the hydrogen electrons are kept in s orbital. And the overlap between two sp orbitals forms a sigma bond, and the remaining sp orbital on each carbon overlaps with hydrogen s orbital to form another sigma bond. Each one of the carbon atoms still has two p orbitals left, and they're perpendicular to each other. And so this overall orbital picture leads to the lateral overlap of these remaining p orbitals. So this would be p1, and this would be p2. Sorry, pi1 and pi2, which means that the total triple bond, of course, it consists of sigma, pi, and pi bond. So a total of 3 bonds which are different in their properties. If we look at the structure of alkyne in terms of bond length, we'll see that this bond is very short. This is 1.20 angstroms. This is about 1.06 angstroms. And this is shorter than in alkenes, where we have 1.33 angstroms. And in alkenes, where we have 1.54 angstroms. Overall, the sigma bond of alkynes is worth about 88 kilocalories per mole. The first pi bond is about 62 kilocalories per mole, and the final pi bond is about 48 kilocalories per mole, adding up to the total value of about 200 kilocalories per mole, which is the total bond strength in the triple bond. So this is a very strong bond. However, even though triple bond overall is very strong, doesn't mean that all of its pieces are very strong. And you can see that the pi bonds are clearly the weakest point in the molecule, and then the ones that react first. And this is what causes a lot of alkyne reactivity to be similar to the reactivity of alkenes, as we'll see at the end of this and the beginning of next lecture. But before we get there, let's focus on something else. If we look at an sp3 hybridized carbon, then you can think of this sp3 orbital as a 25% s and 75% p orbital. For sp2, we'll get 33% s and 67% p. And finally, for sp orbitals, we'll get about 50% s and 50% p. Which means that out of all these orbitals, the sp orbital has the highest percentage of s carriers. Now, what does that mean? That means that s orbitals are closer to the nucleus on average than p orbitals, because p orbitals have a node at the nucleus. So their electron density at nucleus itself is 0, and it's when averaged over the whole orbital, it's still comparatively further away than the s orbital. That in turn means that sp orbital holds its electrons closer than sp2 and sp3 orbital. And in terms of electronegativity, we can classify different types of carbons as having different electronegativities. And those that are sp hybridized are more electronegative than those that are sp2, and these are more electronegative than sp3 hybridized. Now, if we look at the real molecule, that means that if we have a triple bond and then some CH3 group here, that this will be a delta plus end and this will be a delta minus. And perhaps more importantly, if we have a CH bond, then this again would be positive end and this would be negative end. Meaning that the hydrogen has a lot of, is quite polarized in a positive direction, and meaning that this alkyne will be acidic. In other words, the reaction of acetylene, where it releases a proton, will be relatively favorable. I mean, this is pKa for acetylene as an acid is about 25. So this is still a very weak acid. But we have to put this in context. So if we have ethylene, then we can deprotonate ethylene as well, but it's very hard. So this reaction has a pKa which is almost 20 orders of magnitude lower, just 44. And it gets even worse with alkanes, because ethane has a pKa of about 50. So 10 to the 25th times weaker acid than an alkyne. Of course, that's just because alkynes are stronger acids than alkanes, and alkenes doesn't mean that they're really strong acids. So if we compare this to an alcohol or water for that matter, we'll see that the alcohols are much more acidic with pKa's of about 16 to 18. Which means that RO minus is too weak of a base to deprotonate acetylene. But a base that is strong enough would be NH2 minus, which is conveniently prepared from ammonia and sodium. So NH2 minus is strong enough because pKa of ammonia is greater than that of alkyne, 35. So what we can often get is that we have NH3 and we treat this with sodium to get us to NH2, and then treating an alkyne with this will give us ammonia, the gas and leaves, and sodium acetylide. And these compounds are known as acetylides because they're basically acetylene salts. Now, because alkynes are weak acids, it means that these are strong bases. So you will often see this used as a base. But perhaps more importantly, the acetylide anion is not very sterically bulky, and so it can approach carbon-based sites as well, which means that the acetylide is also a strong nucleophile. And this now brings us into a very useful arena, because acetylides have two carbon atoms. They're carbon-based nucleophiles, and they can be used in nucleophilic SN2 reactions just like any other nucleophile, but now with the added advantage that they're creating a carbon-carbon bond. And carbon-carbon bond is really the pinnacle of organic chemistry, because creation of carbon-carbon bonds is how we get from simple molecules to more complex molecules. Therefore, we'll see a lot of the use of alkynes as sources of acetylides and the use of acetylides as nucleophiles in our synthetic problems. And we'll actually see how more complex alkynes can be prepared for simpler alkynes in our next lecture.